Hello, this is the 5-minute Beyond ID9 lightning talk on the alpha to 1 limit of the sharp quantum Rényi divergence, which is a work I did together with Robert and Nilanjana at Cambridge. So let's jump right in. Fawzi and Fawzi recently defined this new quantum Rényi divergence, which you call the sharp quantum Rényi divergence because it has this hash here in the superscript. And it's defined like this. Inside the logarithm here, you have what we call the sharp trace function. It's defined by this convex optimization problem, where you minimize over all positive semi-definite A that also satisfy this constraint where this hash with the subscript is the weighted matrix geometric mean, which is defined like this. They show that this really is a quantum Rényi divergence that satisfies data processing and many other properties. Among them, particularly nice ones and useful ones, is this chain rule, which says that if you look at the divergence between two different channels, each given two different input states, each given a different input state, you get that this is upper bounded by the usual channel divergence, which means you take the supremum over all common input states plus the divergence of the two input states. And this is very useful for showing things in quantum channel discrimination. And then another useful property is that the regularization of this new quantity happens to be equal to the sandwiched. One interesting thing that they didn't show is what happens if you take alpha to 1. So this sharp divergence can easily be seen to be the line between this sandwich divergence and the geometric divergence. And if you take alpha to 1 in both of these, you get 1 to the omega, and for the geometric you get the Belafkin-Stachowski relative entropy, which is defined like this. So you have a different operator ordering here between rho and sigma. And given that these are not equal, maybe an interesting question to see what happens to this sharp if you take alpha to 1. Because you might get a third variant of alpha equals 1 divergence, or you might just get one of these two. And they weren't able to really do something in this direction in the original paper. We managed to solve this problem, and essentially the key step is that we realized that you can think of this sharp trace function and then also the sharp divergence in a slightly different way, which makes things a little bit easier. So what do we do here? Remember, the sharp trace function was given by this convex optimization problem, and here I wrote out the matrix geometric mean. What you can do now here is you can redefine your A. And if you just think for a second that the sigmas are positive definite, you don't need that, but it makes things a little bit easier. Then this new A here, which is given like this, is still going to be positive semi-definite only if the original A was positive semi-definite. So this constraint here doesn't change. And then basically you can kind of shift terms from this constraint here to the thing you optimize over bit by bit. And if you keep doing this, going all the way through, what you're now with is that you find that this sharp trace function is really just minimizing the geometric trace function, the thing that sits inside the geometric Rényi divergence, over all inputs A, which are larger than rho, and you put the A in here. And this directly translates also to the divergence, not just the trace function, because adding the log and the 1 over alpha minus 1 doesn't really change anything. So you have this very nice expression for the sharp divergence. And at this point, calculating the limit isn't that hard anymore, because if you just think about what this limit alpha to 1 of this divergence really is, it's the derivative of the sharp trace function. And now the only thing we really have to do is find a way to exchange the derivative and the minimization. And there's a theorem in that. I quoted here this theorem from the 70s, which basically gives you a bunch of conditions under which you're allowed to exchange the derivative and the minimum. I'm not going to go through it like super in detail, but basically it tells you that if you have certain conditions on the able to restrict the minimization to a compact set, which you can in this case, and you also need some continuity properties, which you also have, then you are allowed to exchange this minimum with supremum. And with this, you then get that this limit alpha to 1 of the sharp divergence is the same as the limit alpha to 1 of the geometric divergence, which happens to be the Belafkin-Stachowski relative entropy. So this may be not like the most sensational result, but I think it's quite a nice, elegant way to show this limit. One final thing, we found that this idea of taking something and then minimizing it over all inputs which are larger actually works quite in general. So if you take any quantum divergence and it satisfies data processing, then if you apply this minimization, you're going to get something else which is also going to satisfy data processing. We showed that. And also, if you take a Rényi divergence, you're going to get back a Rényi divergence and things like this. So like this thing, taking minimums over large input states seems to be something which kind of, is a stable operation. And remarkably also, it seems to give you data processing in certain cases. So, remember that this geometric divergence satisfies data processing only for a certain range of alphas, but the sharp divergence actually satisfies DPI for all alpha larger than 1. So I think it would be interesting to see whether, we show that you can, this always gives you data processing. If you start with data processing, whether, you can maybe make use of these new quantities. And kind of, the first one, which is maybe not trivial, is this what we call Kringanov, the Petz divergence. And I think that's a very interesting open question. Thank you very much for listening to my talk, and if you have any questions, feel free to send me an email.